This is a quick recap video of chapter Thermal Properties of Matter. So let's start with heat. Heat is a form of energy which produces in us the sensation of hotness or coolness. According to the dynamic theory, heat may be regarded as energy of molecular motion, which is equal to the sum of total of the kinetic energy possessed by the molecules by the virtue of their translational, vibrational and rotational motions. Next is units of heat. Calorie is the CGS unit of heat. 1 calorie is defined as the heat energy required to raise the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Like all other forms of energy, the SI unit of heat is joule. 1 calorie is equals to 4.186 joule. Next is joules mechanical, equivalent of heat. Whenever a given amount of work is converted into heat, always the same amount of heat Q is produced. Thus, W is proportional to Q, or we can say W will be equals to JQ, or J will be equals to W upon Q. The proportionality constant J is called joule's mechanical equivalent of heat. It may be defined as the amount of work that must be done to produce a unit quantity of heat. And here J is equals to 4.2 into 10 to the power 7 per calorie, which will be equals to 4.2 joule per calorie. Now next is temperature. It is the degree of hotness of a body. The temperature of a body gives us a measure of the average kinetic energy of its molecules. Thermometer. It is a device used to measure the temperature of a body. It makes use of some measurable properties they are called thermometric properties of a substance which changes linearly with temperature. Next is ideal gas temperature scale. The ideal gas temperature on Kelvin scale is defined by the equation T is equals to limit pressure at triple point tends to 0 to 73.16 in the bracket P upon P. This is pressure and this is pressure at triple point. It is independent of the nature of the gas. Now next is platinum resistance thermometer. It is based on the fact that the resistance of a platinum wire varies with the temperature. If R0 and R are the resistance at 0 degrees Celsius and T0 degrees Celsius respectively, then we can write R will be equals to R0 in the bracket 1 plus alpha T. Here this alpha is the temperature coefficient of the resistance of the platinum and is defined as the increase in the resistance per unit resistance at 0 degree Celsius for 1 degree Celsius raise in the temperature, and alpha is equals to R minus R0 upon R0 into T, and unit of alpha is degrees Celsius inverse. Now if R0 and R100 are the resistances of platinum wire at ice point and stream point respectively, then the temperature Tr of a body for which the corresponding resistance is RT is given by Tr will be equals to RT minus R0 upon R100 minus R0 into 100 degree Celsius. Now next is thermoelectric thermometer. It uses thermoelectric EMF as a thermoelectric property. For the linear part of the thermo EMF, the unknown temperature is given by T EMF will be equals to EMF at T minus EMF at 0 upon EMF at 100 minus EMF at 0 into 100 degrees. Now next is linear expansion. When a solid rod is initial length L is heated through a temperature delta T, its final length increased is given by L dash will be equals to L into 1 plus alpha delta T, where this alpha is the coefficient of linear expansion, and it is given by this expression: alpha is equals to L dash minus L upon L into delta T. The coefficient of linear expansion of the material of a solid rod is defined as the increase in length per unit length per degree rise in the temperature. Next is superficial expansion. When a solid sheet of initial surface area S is heated through a temperature delta T, its final increased surface area is given by S dash will be equals to S in the bracket 1 plus beta delta T, where this beta is the coefficient of superficial expansion, and it is given by beta is equals to S dash minus S upon S into delta T. It is defined as the increase in the surface area per unit surface area per degree rise in the temperature. Now, next is cubical expansion. When a solid of initial volume V is heated through a temperature delta T, its final increased volume is given by V dash will be equals to V in the bracket 1 plus gamma delta T, where this gamma is the coefficient of cubical expansion. It is given by this expression: gamma equals to V dash minus V upon V into delta T. It is defined as the increase in the volume per unit volume per degree raise in the temperature. The coefficient of the cubical expansion of an ideal gas is equal to the reciprocal of its absolute temperature. Gamma is equals to 1 by T. Here you can see. Now, next is relationship between alpha, beta and gamma. The three coefficients of thermal expansions are related as alpha by 1 equals to beta by 2 is equals to gamma by 3, or beta is equals to 2 alpha, or gamma is equals to 3 alpha. The units of alpha, beta and gamma are same as degree Celsius inverse or Kelvin inverse. Now, coefficient of apparent expansion of a liquid. It is defined as the apparent increase in the volume per unit original volume per degree raise in the temperature. Gamma A is equals to apparent increase in the volume upon original volume into raise in temperature. Now, next is variation of density with temperature. Before moving towards this topic, let's understand coefficient of real expansion of a liquid. It is defined as the real increase in volume per unit original volume per degree raise in temperature, and this is given by gamma R, which is equals to real increase in volume upon original volume into that raise in temperature. If gamma G is a coefficient of cubical expansion of the glass material or of the container, then this is the relationship between gamma A and gamma G. Now, next is a variation of density with temperature. The density of a solid or liquid decreases with the increase in temperature. So this is rho dash will be equals to rho into 1 minus gamma delta T. Next topic is specific heat. It may be defined as the amount of heat required to raise the temperature of a unit mass of a substance through 1 degree. If Q heat is needed to raise the temperature of a small m mass of a substance through delta T, then the specific heat C is given as Q upon m delta T. The CGS unit of specific heat is calorie per gram per degree Celsius, and SI unit is joule per kg per Kelvin inverse. Clearly, heat gained or lost is given by this expression: Q equals to mc delta T. Now, next is molar specific heat. It is defined as the amount of heat required to raise the temperature of 1 mole of the substance through 1 degree. If Q heat is needed to raise the temperature of n moles of the substance through delta T, then the molar specific heat C is equals to Q upon n delta T. The CGS unit of molar specific heat is calorie per mole per degree Celsius, and the SI unit is joule per mole per Kelvin inverse. Next is heat capacity or thermal capacity. It is defined as the amount of heat required to raise the temperature of a body through 1 degree. heat capacity is equals to mass into specific heat, which will be equals to m into c. The CGS unit of heat capacity is calorie per Celsius inverse, and SI unit is joule per Kelvin inverse. CGS unit and here SI unit. CGS unit is equals to calorie for the heat capacity or thermal capacity, calorie degree Celsius inverse, and SI unit is similarly joule Kelvin inverse. So next is water equivalent. The water equivalent of a body is defined as the mass of the water which requires the same amount of heat as is required by the given body for the same rise in the temperature, which is given as W will be equals to mass into specific heat, and similarly which will be equals to mc. And the CGS unit of water equivalent is gram, and the SI unit of water equivalent is kg, as this is weight. So now next is latent heat. The amount of heat required to change the state of unit mass of a substance at a constant temperature is called latent heat. It is denoted by L. Now next is latent heat of fusion. The amount of heat required to change the state of unit mass of a substance from solid to liquid at its melting point is called latent heat of fusion. Next is latent heat of vaporization. The amount of heat required to change the state of unit mass of a substance from liquid to vapor at its boiling point is called latent heat of vaporization. Next is principle of calorimeter. When two bodies at different temperature are placed in contact with each other, the heat lost by the hot body is equal to the heat gained by the cool body. This principle of calorimeter or principle of this is also known as principle of mixtures. So heat gain will be equals to heat lost. Next is transfer of heat. The three modes of transfer of there are three modes of transfer of heat. First is conduction, second is convection, and third is radiation. So let's start with conduction. It is the process in which heat is transmitted from one part of the body to another part at lower temperature through molecular collisions with any actual flow of matter. Now let's understand steady state. The state of the rod when the temperature of every cross section of the rod becomes constant and there is no further absorption of the heat in any form or any part is called steady state. Now next is factors on which conduction of heat depends. When two opposite faces of a slab, each of area of cross section capital A and are separated by a small distance x, are maintained at temperature T1 and T2, where T1 is greater than T2, then the amount of heat that flows in time T will be given by capital Q will be equals to Ka in the bracket T1 minus T2 into small t upon x, where this capital K is the coefficient of thermal conductivity of the material of the slab between its two faces. The rate of flow of heat through the slab dq upon dt will be equals to minus K A dt upon dx. Here this dt upon dx is the rate of fall of temperature with distance and is called temperature gradient. Next is coefficient of thermal conductivity. It may be defined as the quantity of heat energy that flows in unit time between the opposite faces of a cube of unit side, the faces being kept at 1 degree difference of temperature. Its CGS unit is calorie per second per centimeter per degree Celsius, and SI unit is joule per second per meter per Kelvin. And now dimensional formula of K is, let me write here, mlt minus 3k minus 1. This is the dimensional formula for this. and thermal conductivities of metals are much greater than those of metals. Gases are poor thermal conductors. Now next is heat, current and resistance. The flow of heat per unit time and conduction is called heat current, and the ratio of temperature difference between the ends of a conductor to the heat current through it is called thermal resistance. Now the heat current H is equals to Q upon T, which will be equals to K A del T upon del X. Thermal resistance RH equals to del T upon del H, this is H, and which will be equals to del X upon K A. SI unit of RH is this, and dimensional formula is this. Now next is convection. It is the process by which heat is transmitted through a substance from one point to another due to the bodily motion of the heated particles of the substance. Fluids are mainly heated through convection. Natural convection arises due to unequal heating and gravity. When more heated and less dense parts raise and are replaced by the cooler parts of the fluid in forced convection, a material is forced to move by an agency like a pump or a blower. Now next is radiation. It is the process by which heat is transmitted from one place to another without heating the intervening medium. Next is Prevost's theory of heat exchange. All bodies emit radiations irrespective of their temperatures. They emit radiations to the surrounding and receive radiations from the surroundings. In the equilibrium state, the exchange of energy between a body and its surrounding occurs in equal amounts. Now, thermal radiation. The electromagnetic radiation emitted by a body by virtue of its temperature is called thermal radiation or radiant energy. Thermal radiations are electromagnetic waves of wavelength ranging from Now next is absorption power or absorptivity. It is denoted by small a lambda. The absorptive power of a body for a given wavelength lambda is defined as the ratio of amount of heat energy absorbed in a certain time to the total heat energy incident on it in the same time within a unit wavelength range around the wavelength lambda. It is dimensionless quantity. Next is emissive power, which is represented by small e lambda. The emissive power of a body at a given temperature and for a given wavelength lambda is defined as the amount of radiant energy emitted per unit time per unit surface area of the body within a unit wavelength range around the wavelength lambda. Its SI unit is, or this can be written as. Now next is emissivity. It is the ratio of emissive power of a body to the emissive power capital E of a black body. Here let me write first. This equals to E upon E. So this is the emissive power of a body and this is emissive power of a black body at the same temperature. It is dimensionless quantity having the value between 0 and 1. The emissivity of a black body is 1. Now let's understand what is black body. A black body is one which neither reflects nor transmits but absorbs whole of the heat radiation incident on it. The absorptive power of black body is unity. Next is Kirchhoff's law. It states that at any given temperature, the ratio of the emissive power this to the absorptive power this corresponding to a certain wavelength is constant for all the bodies, and this constant is equal to the emissive power of the perfect black body, this E lambda, at the same temperature and corresponding to the wavelength. So this is the expression. Hence, a good absorber is a good emitter. Now next is Stefan-Boltzmann law. It states that the total amount of energy radiated per second per unit area of a perfect black body is directly proportional to the fourth power of the absolute temperature of the body. So E is proportional to T to the power 4, or E is equals to sigma T to the power 4, where this sigma is called Stefan's constant. Now its value is 5.67 into 10 to the power minus 5 per second per centimeter. This is centimeter to the power minus 2, Kelvin to the power minus 4. So, and another in SI, this is for CGS, and this is for SI system. This sigma equals to finally you will get 5.67 into 10 to the power minus 8 W m to the power minus 2 k to the power minus 4. So if a perfect black body of at temperature capital T is placed in an enclosure at temperature T naught, then the net amount of energy radiated per second per unit area by the black body is given by this. E will be equals to sigma T to the power 4 minus T naught to the power 4. And if a black body and the enclosure are not perfect black bodies and have relative emissivity, then this is the equation representing the same. E will be equals to epsilon sigma T to the power 4 minus T naught to the power 4. Next is Newton's law of cooling. For a small temperature differences between a body and its surroundings, the rate of cooling of a body is directly proportional to the temperature difference and the surface area exposed. This is known as the Newton's law of cooling. dt upon this is capital T and this is small t equals to minus Ka in the bracket T minus T naught. So next is Wien displacement law. It states that the wavelength, this lambda m, corresponding to which the energy emitted by a perfect black body is maximum, is inversely proportional to the absolute temperature of the black body, and this is the equation. So, or we can write in this form. After removing the proportionality sign, we use a constant b, and the value of b, it is known as the constant of proportionality, and it's also called Wien's constant. It is its value is 2.9 into 10 to the power 3 meter Kelvin. Now next is solar constant. It is defined as the amount of solar radiant energy that a unit area of a perfect black body on the earth would receive per second in the absence of the atmosphere, with its surface perpendicular to the direction of the sun rays, and its value is 1340 W m to the power minus 2. Now next is surface temperature of the sun. If S0 is a solar constant, Rs the solar radius, and R0 is the mean distance of the earth from the sun, then surface temperature of the sun will be T will be equals to in the bracket R0 square S0 upon Rs square sigma to the power minus this is 1/4. So that's all in this chapter. Thank you.